Hi, welcome to the solutions for Ready, Set, Go, Unit 3, Lesson 9. Is this the end? So the Ready section just wants us to multiply. So I'm going to take every term in the first set of parentheses and multiply it by the terms in the second set. So x times x is x squared. X times 5 is 5x. So now let's go to our plus 5 and distribute that. So we have a plus 5x again, and 5 times 5 is 25. Now let's combine our like terms to get x squared plus 10x plus 25. Okay, so moving on to question 2. So x times x is x squared. X times minus 3 is negative 3x. Negative 3 times x is negative 3x again. And negative times negative is positive. 3 times 3 is 9. So we combine our like terms to get x squared minus 6x plus 9. Okay, lastly here, a times a is a squared. A times b is plus ab or ba. The order doesn't matter. So b times a is plus, I'm going to write it as ab so that I keep the same order as before, but ba is okay as well. B times b is b squared. So we do have some like terms here, right? AB are like terms, so I can make that 2ab plus b squared. Okay, so we have multiplied. Now, question 4 says, in problems 1 through 3, the answers are called perfect square trinomials. What are the features of the perfect square trinomial? So if we noticed that the first and last term, the x squared term, so the x squared term, the first and last terms are perfect squares. And what I mean by that is, like, the 5 times 5 created the 25. 3 times 3 created the 9. B times b created b squared. So I could take the square root of each one of those numbers, and it comes out to a perfect number. And the middle term, so the middle term now notice that we actually got the same term twice. 5x plus 5x minus 3x plus minus 3x. AB plus AB. So is doubled, essentially. So the middle term comes out to itself, but doubled. So let's find a nice way to phrase that. So the middle terms match. I'll say the middle terms match. So they are doubled when combined. Now this is all so when written in descending order. When written in descending order. So it gives us, so what it gives us is, and I'll use this one here kind of really, is that it's this a squared, and it'll always be positive because we're multiplying two things by each other, so it's going to come out to positive. This middle term is positive or negative. And this last term will always be positive. So that's going to produce a squared plus or minus 2ab plus b squared. So that's the form of a perfect square trinomial, that we can kind of always assume that these two are going to have the same sign, so we can double them. We can make that 2. It can be positive or negative, where all the other terms will be positive. Okay. So question 5, we're back to multiplying. So x times x is x squared. X times negative 8 is minus 8x. And then positive 8 times x is plus 8x. And 8 times negative 8 is minus 64. So let's combine our like terms. Negative 8 and positive 8 add to 0. So we're just left with x squared minus 64. Let's go down to problem 6. So x times x gives us x squared, and x times negative root 3 gives us negative root 3x. Okay. Positive root 3 times x gives us positive root 3x, and you can put the x in front if you want. And then negative root 3 times positive, so negative times positive is going to be a negative. Root 3 times root 3 just becomes root 3. If you want, you can think of it as root 9 first, and then get your 3. But if you multiply a square root by itself, the square root sign disappears. It undoes itself. So let's combine our like terms. Right here are our like terms. One's positive, one negative. So they add to 0. Oops, I wrote a 3. X squared minus 3 is our final simplified answer. So question 7, we have x plus b times x minus b. So x times x is x squared, and x times b is negative bx. B times x is positive bx, and b times negative b is negative b squared. So again, we have like terms in the middle that add to 0. So x squared minus b squared. So question 8 says the products in problems 5 through 7 end up being binomials. They are called the difference of two squares. What are the features of the difference of two squares? Okay, so the difference of two squares. Well, that word square is coming from the fact that we always end up with two terms. So difference of squares, we end up with two terms. With a minus sign between them. And both terms are perfect squares. Now, that one, it doesn't actually have to be a perfect square. For instance, if we look at our example from question 6, 3 does not have a perfect square root, but we can write it as the square root of 3, which does become perfect. So, yes, we can always do this as long as there's a minus sign. We just might have to have a square root symbol in our factor. Now, this one has a part B. It says, why don't they have a middle term like the answers to problem 1 through 3? Well, since that middle term is the same term with opposite signs, the middle terms add to zeros. The middle terms add to 0, which we don't have to write. We actually could write it with the third term with a 0 in there, but that wouldn't count as, that wouldn't make it a trinomial because my 0 could be added to the constant number. Okay, anyways, let's go back to multiplying now. So here we have a binomial times a trinomial. So we're going to keep our same strategy. We're going to take we're going to take this x and multiply it by every term in the second set of parentheses. So we get x cubed times 3, or plus 3x squared. And then x times 9, so plus 9x. So now I'm going to take my 3 and distribute that. So I'm actually going to do this as 2 lines instead of 1. I could do it as one long line, but I like to kind of stack them. So negative 3x squared minus 9x minus 27. So when I combine those terms, right, the x cubed is still there, but these go away, and these go away, and left with minus 27 at the end. Okay, let's go to problem 10. So problem 10, x times x squared gives us x cubed. X times negative 10x gives us minus 10x squared. And x times 100 gives us plus 100x. I'll do this one in a horizontal fashion this time instead of vertical, just so if you prefer that method, you see both. So here 10 times x is plus 10x squared. 10 times negative 10x is negative 100x. And 10 times 100 is 1,000. So let's combine our like terms. 10x squared, positive 10x squared, negative 10x squared, positive 10x squared, add to 0, and 100x and negative 100x add to 0, so we're left with just x cubed plus 1,000. Okay, now let's go to problem 11. So, a times a squared gives us a cubed. A times minus ab gives us negative a squared b. And a times positive b squared gives us positive a b squared. Okay, now if I distribute my b, I get plus a squared times b. And then b times negative ab becomes negative a b squared. And then b times b squared gives us plus b cubed. So again, let's combine our like terms here. We have negative a squared b and positive a squared b. So those add to 0. We have positive ab squared and negative ab squared. So we're only left with a cubed plus b cubed. And there's problem 11. So let's go down to problem 12. So problem 12a says, the work in problems 9 through 11 makes them feel like the answers are going to have a lot of terms. What happens in the work of the problems that makes the answers be binomials? Okay, so for this problem, instead of handwriting this out, I have some typed answers here, right? When the binomial and the trinomial are multiplied, the terms in the middle are always the same with opposite signs, right? We notice that for all these patterns that we had that negative 10x squared plus 10x squared. We had that plus 100x minus 100x, or, that plus 3x squared minus 3x squared plus 9x minus 9x. So the terms ended up being the same, which means they added up with opposite signs. So they added up to 0. But we have to be careful. That's not true for any binomial times trinomial. They have to be in this form of a cubed plus b cubed, or a cubed minus b cubed. So if I look at my numbers above, I can see that, well, let's come down here. Let's break down this form a little. So notice that b squared, a squared, a squared. We have that plus ab minus ab, in this a minus b, a plus b. So the final answer, so this is what we found. We found this final answer. So if we looked at our final answers, they were all, could be written as something cubed. The last one, a cubed plus b cubed. But here, this could be written as x cubed minus 3 cubed. So it fits that form there, right? And here, where's the middle one? There we go. Our final answer here could have been x cubed plus 10 cubed. So they all fit that form, as I can write that answer as something cubed minus something else cubed, or something cubed plus something else cubed. So they fit that form. Okay. Now, part B says, these answers are called the difference of two cubes, which we saw in problem 9, and the sum of two cubes, which is problem 10 or 11, right? So number 9, we saw a minus sign in between, so that's why it's called a difference. In 10 and 11, we see that there's a plus sign in between, so those are the sum. So, difference in the sum. What about these answers makes them the sum or difference of cubes? So again, let me just put in some typed work here instead of writing this whole solution. It'll be a little faster for you all. So the solutions for problems 9 through 11, which are written like x cubed minus 3 cubes, I showed that above, and x cubed plus 10 cubes, and a cubed plus b cubed. It's a lot easier to see that the first and the last numbers are raised to the third power when we write them as instead of x cubed minus 27, and instead of x cubed plus 1,000, right? So it's either an addition sign or a subtraction sign in the middle, and that's the difference between them. That is their addition or subtraction sign. If there's a difference, we use the sum of two cubes formula, and if it's a subtraction, we use the difference of two cubes formula. Okay, let's move on to question 13. So question 13 says, state the y-intercept, the degree, and the end behavior for each of the given polynomials. So y-intercept, when it's in this form, is actually really quick because all these terms with x are going to go to 0. And we're just going to be left with the constant number at the end, because y-intercept means x equals 0. So f of 0, right, we could actually plug it in, and I'll do that for this first one. 7 times 0 to the 4th minus 9 times 0 cubed plus 0 squared minus 13 times 0 plus 8. Those all go away, and we're just left with 8. So our y-intercept is 0, 8, or f of 0 equals 8, if you like to use that function notation. So the degree, when it's in standard, so let's note that this is in standard form, meaning it's the highest exponent is written first, and we have a sum or difference of our terms. So our highest exponent is the degree. So now the end behavior, as x goes towards negative infinity, right, as x goes towards the left, what is happening to our y? Well, for this, we need to not just think of the degree, but also the leading coefficient. So our leading coefficient in this case is the number in front of x to the 5, which is just a 1, a positive 1. So if it's positive and odd, we're going to definitely have sort of this type of end behavior. Positive leading coefficient and odd degree. So as x is going to the left, notice we're going down. So down means we're going towards negative infinity. Here, as x goes towards the right, as it goes towards positive infinity, our graph is going up. So it's going towards positive infinity. So that's our end behavior. Okay, number 14, our y-intercept. Again, all these terms will go to 0. So our y-intercept is 0, negative 15. It's going to be that constant number at the end. So let's go down to our next parts. It says, what is the degree? Well, again, this is in standard form. So we see that the leading term, I'll write it down here. Our leading term is 3x to the 4th. So a degree is 4. And since we're positive on the leading coefficient, that means we're going to have a shape something like that, right? That's not actually what it's going to look like, but we see that it's both up. So they're both ending up. So whether x is going to the left or the right, since it's an even degree, it's going to go in the same direction. Since it's positive, it's going to go upward. So they're both going up. So g of x is going to approach infinity. So as x approaches negative infinity, g of x approaches infinity. As x approaches positive infinity, g of x also approaches positive infinity. Okay. Question 15. So y-intercept, there's a plus 0 at the end here that we don't see. So our y-intercept is 0, 0. All those terms, that x to the 9th becomes 0, and that x squared becomes 0. So our degree, well, again, our leading term, oh gosh, that's term, there we go, is negative 7x to the 9th. So our degree is 9, but this time our leading coefficient is negative. So it's going to end in opposite directions, but it's going to kind of have this shape to it. And there's going to be some curves and bumps and whatnot. Well, that part we'll get into later, but it's going to have this up and left and down and right. So as we're going to the left, our graph is going towards positive infinity. So as x approaches negative infinity, h of x approaches positive infinity, right? We're decreasing over the length of our graph. There might be some bumps where it increases temporarily, but overall we're decreasing. So as we go to the right, we're going to be going down towards negative infinity. So as x goes towards positive infinity to the right, we're going downward. So h of x goes towards negative infinity. So there's our end behavior. Okay, so question 16. Our y-intercept, we notice that we have our x terms. Those are going to go to 0. So our y-intercept is 0, 4. Our degree is 2. So since our leading term is 5x squared, so it's positive, we're going to end upward. So it's going to look something like that. So as x goes towards the left, as x approaches negative infinity, p of x also approaches positive infinity. I'm sorry. As x goes to the right, or x approaches positive infinity, p of x approaches positive infinity as well. So they are both up. Okay. Question 17. So y-intercept, I see my x terms, which means there is my y-intercept, my constant number at the end, 0, negative 20. Okay, so now let's talk about the degree. It's in standard form, so our degree is 3, right? Our leading term here is just x to the third, right? So it has a positive leading coefficient, which means it's going to look something like this. It won't be that exactly, but it looks something like this. So as x goes towards the right, we're up, and as x goes towards the left, we're down. So as x goes towards negative infinity, that's our left side. I'll write left. We're going downward, so negative infinity. As x goes towards positive infinity, q of x goes towards positive infinity. Okay, question 18. We have just a regular linear equation here, but we can see our y-intercept is 12. And it's in that y equals mx plus b form, if that helps you recognize it. But it's the same pattern we've been using, where any term with x is gonna go away. It's gonna turn to 0. So we're just left with our 12. Our degree here is 1, right? The exponent on that x is a 1. So our leading term is negative 4x to the first power. So we're going to have a linear equation here, because x, so there's going to be no curves or bumps, and it's decreasing. So it's going to look something like, and I'll do it a little bit more accurate since we know that the y-intercept is 12, so it's going to be up there. But as we go left, we're up. So as x goes towards negative infinity, y goes towards infinity. And the rest of it is down here. As x goes towards positive infinity, so it goes to the right, we're going down. So y goes towards negative infinity. I didn't put my negative sign in there. Negative infinity. So there's question 18. Okay, so question 19. Identify each function as even, odd, or neither. So for it to be even, right, it's symmetric over about y, let's say the y-axis. I'll put the y-axis. The y-axis. For it to be odd, it's symmetric about the origin. Meaning y equals x. You could also think of this as, so for even, you can think of f of x has to equal f of negative x, and it doesn't matter which side of that y-axis is on, the output should be the same. And for odd, f of x has to equal negative f of negative x, that the axis side is going to be the same, but flipped to the other side of the x-axis as well. So it's symmetric about both the x and y axis. Really. Okay. So let's look at our first one. Right here's our y-axis, and I can see that looks identical on both sides of the y-axis, so this is an even function. Here again, here's our y-axis. It looks symmetric on both sides of that y-axis, so a and b are both even functions. Now this one, even though all a, b, and c are all quadratics, this one is not symmetric about the y-axis. Its axis of symmetry actually looks to be axis of symmetry is x equals -1, not x equals 0, right? Y-axis, another way of phrasing that is x equals 0. So it is neither. It's definitely not odd because we don't see it going in both directions. So that one is neither. So this one, it's not even. It's certainly not symmetric about y equals the y-axis. Let's see if it looks symmetric about the origin. So I'm going to dot this on here. So we see that like where we have maybe -1-ish right around there, -1, -1, and then we have a +1, +1. So if we switch our x and our y, so switch sign of both. X and y, and the graph does not change. That makes this odd. And that looks like it holds true throughout, right? Even up here, something a little bit more than 2, +2, hits right around y equals 5. So here, we're seeing that same thing, negative, something a little bit less than -2, or more than -2, I should say, is right around -5. So this one is definitely giving us odd. Okay. E. Did we miss? No, that was D. Okay, so E. So this one, here's our line of symmetry, and I can see it's definitely not reflexive over that line. So this one is neither. It's not even or odd. And here again, it is not reflexive over that line, so we have a neither for F. All right, let's move on to our Go problem. So question 20. It says fill in the conjugate of the given expression, then multiply the two conjugates. So conjugates, we want that I term to essentially go away entirely. So conjugate, we're going to switch the sign in the middle. And that's all we're going to change. We're creating, ready, we create a difference of squares. So that's what we're creating, because we know with the difference of squares that we're going to get a squared term to start and a squared term to end as a binomial, right? So let's actually multiply these. We could use our difference of squares shortcut, but I'll actually show it the whole thing out. So we get 121 minus 44i, and then we get plus 44i. So those I terms are going to cancel out, which is great. And then -4 times +4 is going to be -16, and I times I is I squared. So let's combine our like terms. Remember that I squared is the same thing as -1, right? The square root of -1 is I. So if I square both of those, and I'll write them on the same side. So I equals the square root of -1. So if I were to square both of these, the square cancels out and I'm left with I squared equals -1. So I can replace any -1 I see with, or any I squared I see with -1. So those add to 0. So 121, well, -16 times -1 becomes +16. And now because those are both constant numbers, we can add those together. So we get 137. Okay, awesome. Question 21. The conjugate of this one we only actually need to do, we only need to get rid of the I. So if we were just trying to rationalize this in a fraction, we would just need to multiply by I because it specifically says conjugate. We can think of this as 0 plus 9 if you want, like 0 plus 9, which means we do 0 minus 9i, or just negative 9i. So that becomes negative 9 times, positive 9 times negative 9 is 81. I squared. Remember, the I squared is equivalent to negative 1. So negative 81 times negative 1 gives us positive 81. Okay. 2 minus 13i, the conjugate is going to be 2 plus 13i. So if we multiply these, 2 times 2 is 4. 2 times 13i is 26i. Negative 13i 2 times 2 is negative 26i. And then negative 13 times positive 13, that's negative 169 I squared. So now let's combine our like terms, right? Those reduce, they go to 0. So we're left with 4. And this becomes plus 169, which when we add 4 to it becomes 173. Okay, so 23. So if I have a minus 4i, if I want to multiply by the conjugate, I want to switch the sign. So I want to use a positive 4i. So negative times positive, negative 16i squared, which turns to be positive 16. So that one's pretty quick. Here I'm going to keep my first term the same, negative 1. I'm going to make this a plus 2i. So when I multiply negative 1 times negative 1, I get positive 1. And then I get minus 2i. Okay, negative 2i times negative 1 gives us a positive 2i. And then negative 2i times positive 2i gives us minus 4i squared. So let's combine those like terms. Again, those reduce to 0. So 1, and this becomes plus 4. So we end up with 5. Okay, question 25 asks us to solve for x. Okay, so let's think about this one. We have x squared plus 10 equals 0. So this is a quadratic, but it's only two terms, right? There's no x term. There's no linear term here. Oops, sorry, I moved the whole screen. So we can go ahead and get this, isolate x squared. So I'm going to move this positive 10 over to the other side. So I'm going to get x squared equals negative 10. Now to get rid of my square, I want a square root. But whenever I square root, I do have to be careful. I want to do plus or minus the square root. So I get x equals plus or minus the square root of negative 10. Well, the square root of negative 10 can become x equals plus or minus I root 10. There we go. Okay, here I'm going to move that 7 over to the other side. So x squared equals negative 7. Once again, I'm going to take the square root of both sides. And when I do that, I do plus or minus. So x equals plus or minus, since I have a negative under the radical, I'm going to make that I root 7. There's question 26. 27 does have a linear term, and so does 28. So for these ones, we're going to go about it a little differently. Let's do the quadratic formula. So let's have a is 1, b is also 1, and c is 1. So we have a lot of 1s. I always like to do my discriminant first, my b squared minus 4ac first. So b squared is 1 minus 4 times a is 1 and c is 1. So I get 1 minus 4, which is negative 3. So this tells me that we're going to have no real solutions, but there is a solution. So quad formula, right, is x equals negative b plus or minus the square root of our discriminant, b squared minus 4ac, all divided by 2 times a. So we already did the b squared minus 4ac part. So let's do negative b. So negative 1 plus or minus, well, we already figured out that b squared minus 4ac is negative 3 over 2 times a. So we can simplify this a little bit more, right? I can take out, instead of just doing, let me kind of write it like this, x equals negative 1. Instead of having a square root of negative 3, I can take out the I. So I root 3, and 2 times 1 is just 2. So there we have it. You can write those as two separate terms if you want, as negative 1 plus I root 3 over 2, and then negative 1 minus I root 3 over 2. But I'll leave it as a plus or minus right now. Okay, here, 28, our a is 1, our b is 1, and our c is 2. So this time b squared minus 4ac is 1 squared minus 4 times 1 times 2. So 1 minus 8, or negative 7. So x equals negative 1, because that's our b value, plus or minus negative 7 over 2 times 1. So there's nothing much to reduce here except for my imaginary value there. So negative 1 plus or minus I root 7 over 2. We'll leave it like that. You could do the decimal approximation of I. Let me read the directions one more time. It just says solve for x, so we'll leave it as radicals. They're more exact anyways. And that is the last problem on this Ready, Set, Go. So hopefully this was helpful, and thank you for watching.